Okay, let's unpack this.
Yeah.
We hear all the time about algorithms making these huge decisions for us, approving loans, flagging fraud, even recommending medical treatments.
Right.
But how does a computer actually um, learn to make a judgment call? How does it go from just a pile of raw data to a definitive yes or no?
That is precisely our mission for this deep dive. We're deconstructing the source material on the mechanics of these digital decision makers.
We're really getting into it.
We're looking at the core concepts of classification and machine learning, and critically, the validation methods you absolutely need to make them trustworthy.
So classification, at its heart, it seems deceptively simple.
It is.
It's the process of learning a model that predicts a discrete class label. It's not trying to predict a number, like a stock price. It's a category.
Exactly. Like, is this transaction legitimate or is it fraudulent? Is this tumor benign or malignant? Or even, is this news article about finance or sports?
It all starts with data, where you already know the answer, the training set.
Yes, the training set. But the real challenge, the whole point, is to build a model from that training data that can then accurately assign labels to things it has never seen before.
Which brings us right to the first sort of technical commandment, doesn't it?
Yeah.
You have to separate what you know from what you don't.
You absolutely have to. We always divide the labeled data. The training set is for building the model, and then the test set is kept completely separate, just to give the model a final impartial grade.
No cheating.
No cheating. The two must never touch.
Okay, so let's dive into the nuts and bolts. We're going to focus on one of the most powerful and intuitive methods for this, the decision tree.
It's a great place to start. I mean, there are many others, neural networks, logistic regression, but a decision tree gives you this really clear visual logic.
Like a flowchart.
Exactly like a flowchart. And the whole workflow breaks down into two main stages: induction and deduction.
Induction sounds like the heavy lifting part.
It is. Induction is the learning process. It's where an algorithm, something like Hunt's algorithm, uses that training set to figure out the structure of the tree. What questions to ask and in what order.
And then deduction is the easy part.
Deduction is the application. That's when we take a new sample, something totally unseen, and we just drop it into the top of the tree we built.
And just follow the branches down.
Follow the branches down until you land on a leaf node. And that leaf gives you the answer: fraudulent or legitimate.
Let's use that classic example from the sources. Trying to predict if someone will cheat on their taxes. You've got attributes like marital status, if they got a refund, their income.
Right.
When you're building that tree in the induction phase, how does the algorithm know when to just stop? When is a branch finished?
Well, the process is recursive, so it's just applying the same logic over and over. And the first stopping rule is really simple. We can call it the purity rule. Yeah. If all the training records at a certain spot in the tree, a node, belong to the same class, say everyone who got a refund also cheated, then that node is perfectly pure.
So it's found a definite answer.
It's a definite answer. It becomes a leaf node, and that branch is done.
But what if it's a mix? A messy, impure node?
Then the algorithm has to split the data. It applies an attribute test, a question like, are they married, to split that messy data into smaller and hopefully purer subsets. Then it just repeats the whole process on those new, smaller groups.
So the goal is always to get to that perfect purity. But here's the big question. If you have, say, 3 different attributes you could split on, how does it decide which question is the best one to ask first?
That's the key. It uses what's called a greedy strategy.
Greedy.
Greedy. At every single node, it only looks for the one attribute test that gives it the best immediate improvement. It's always making the locally optimal choice.
Wait a second. If it's only looking for the best immediate split, couldn't it miss a much better path, 5 steps down the line? It feels short-sighted.
That is a fantastic and critical point, and yes, it absolutely could. The greedy approach means it sacrifices finding the perfect, globally optimal tree for computational efficiency.
So it's a trade-off.
It's a huge trade-off. Searching for the theoretically smallest tree is just. It's computationally massive, impractical. So by focusing only on the best immediate gain, the system stays efficient.
So this gain, this improvement, all comes down to measuring the impurity of a node.
Precisely. Node impurity is just a mathematical score for how mixed up the classes are. High impurity means you have a messy 50-50 mix. Low impurity means you're getting close to a clear answer.
And what are the tools for measuring that? How do you put a number on the chaos?
There are a few, like entropy and misclassification error, but the sources really highlight the Djani index. It's used in really common and powerful algorithms.
The Gini index. Okay, so what does that number actually tell us?
Its range is what makes it so useful. A Gini index of 0 means perfect purity, 0 chaos. All the records in that node belong to a single class. The decision is certain.
And the other end, maximum chaos.
Maximum chaos. For a two-class problem, if the records are split exactly 50-50, the Gini index is 0.5. Total indecision.
So at every step, the algorithm calculates the Gini for splitting on every possible attribute and picks the one that causes the biggest drop in that Gini score.
That's the whole game. That drop is the gain. You find the question that delivers the highest gain.
Okay, that seems straightforward for things like marital status, where you have a few clear options. But what about a continuous attribute, like taxable income? You can't test every single possible dollar amount.
You can't. And this is where a really classic efficiency hack comes in. You don't have to check every number.
So what's the trick?
First, the algorithm sorts all the values for that attribute, from lowest to highest.
Okay, why sort them?
Because the best possible split point will always be between two adjacent data points that belong to different classes.
Yeah.
By sorting, the algorithm just has to do one quick linear scan. It only calculates the Gini for a handful of potential split points. It's incredibly fast.
That is a brilliant time saver. So, okay, we've built the tree, we've optimized every split, but how do we actually know if the final model is any good?
And now we pivot to the most important part, model quality, which is all about generalization.
Generalization.
Does it correctly predict the labels for data it's never seen? That is the only true test.
And here's the paradox that always trips people up. The sources are so clear on this. You can almost always get 100% accuracy on your training set if you make the tree deep enough. But is that the goal?
And the answer is a huge, resounding no.
It's the biggest trap.
It is. Getting 100% on your training data usually means you've fallen into a trap called overfitting. The model hasn't learned the real pattern. It has just memorized the training data.
Including all the random noise and errors.
Every single bit of noise. It's like a student who memorizes the answer key from last year's test, typos and all, but has no idea how to actually solve a new problem.
Right, and then when it sees new data, it just completely falls apart.
Its performance plummets. And that's the opposite of underfitting, where the model is way too simple and misses the pattern entirely. You're always looking for that sweet spot in the middle.
What actually causes overfitting? Is it just making the tree too complex?
It's a mix of things. The sources point to noise points, data that's just weird or mislabeled. The algorithm twists itself into knots trying to perfectly account for those outliers.
And not enough data.
And not enough examples in certain areas. If the model only sees, say, 3 data points in some corner of the data space, it will create a really specific and probably meaningless rule just for those 3.
Which is where that old philosophical idea, Occam's razor, comes in.
Absolutely. Occam's razor is a core principle here. It says if you have 2 models that perform about the same on new data, you have to prefer the simpler one.
Because the complex one is more likely just fitting to random noise.
Exactly. Simplicity is robustness.
So how do you enforce that simplicity? The solution is something called pruning.
Right. And there are 2 main ways to do it. The first is pre-pruning or early stopping.
So you just stop the tree from growing too big in the first place.
You set rules, like you stop splitting if a node has too few examples or if a split doesn't really improve your Gini score by much.
And the other approach is post-pruning. This one sounds a bit weird. You build the whole massive overfitted tree and then you chop bits off.
It does sound counterintuitive, but sometimes you need to let the tree grow deep to even find certain patterns. Post-pruning lets you do that, and then it corrects after the fact.
So you grow the whole thing out.
You grow the full tree, then you work backwards from the bottom up. You test whether trimming off a whole subtree and replacing it with a single leaf actually improves the model's performance on unseen data. If it does, you make the cut.
It's like trimming a hedge. You let it grow out and then cut back the messy branches.
That's a perfect analogy. And that whole process relies on having a good way to measure performance, which brings us to evaluation metrics.
And simple accuracy, just the percentage you got right, can be really misleading.
Oh, dangerously misleading. The sources give a great example. Imagine you're looking for a rare disease that only affects 10 people out of 10,000.
Okay, so you have 9,990 healthy people and 10 sick people.
Now, imagine a completely useless model that just predicts everyone is healthy.
Well, it would get 9,990 predictions right and only 10 wrong. That's 99.9% accuracy.
99.9% accuracy. And it is completely worthless because it failed to find a single case of the disease we actually care about.
So we need a better tool than just accuracy.
We need the confusion matrix.
Yeah.
It's the standard diagnostic tool. It just maps the actual class versus the predicted class.
And it gives you those 4 crucial outcomes.
The bedrock of prediction. You have your 2 correct outcomes. True positives where you correctly said yes, and true negatives where you correctly said no.
And then the 2 errors, false positives, where you said yes, but it was no, the false alarm.
Right, and false negatives